Okay, I'm going to do two more things today in the lecture regarding computations. I'm going to cover, yesterday we talked about significant figures, and that's what Dry Lab is about, along with scientific notation, and along with using scientific notation in operations, particularly complex operations. I want to continue with that today, and then we get into problem solving. Now, this is some of the problems that the people from yesterday's lab had some challenges with. And what I want to do is talk to you about how to do this on a calculator that's got an EE function and a calculator that does not. I really think a calculator with EE function on it saves you at least 5 keystrokes per entry. And if you've got something like this, you're looking at 555, that's 15 keystrokes. And each time you save a keystroke, the odds of you making an error is going to be less. Okay, so let's look at how to do this now. By the way, the program I'm using is OneNote by Microsoft. Up in Washington, they standardized this and was able to integrate actually into Canvas. So that as I was doing this, you could be logged into Canvas and actually see this in real time as I'm doing it. It was a real pain to set up, but once you got it set up, it was really slick. Okay, so how would I do this program? Okay, first of all, there are 2 ways to do this program, actually 3 ways, but one way is to do this stepwise. So in other words, you're going, oh, there's a multiplication on the bottom. I'm going to do that and then write that answer down. And then I'm going to take 1.2 times 10 to the 6th and divide it by that answer down here. Okay, that's one way. That, in my opinion, that's the least desirable way because that leads to the most clerical errors. Now we can do that whole thing inside this calculator and it'll keep it internally. The calculator has about 29 significant figures underneath the covers. And this problem has, how many sig figs does this problem up here have? Our answer is going to have how many? 2, because we have 3 there, 2, so our answer is going to be in 2. Now, sometimes people, when they do intermediate answers, they round. They go, oh, we have 2 sig figs, I'm going to round to 2 sig figs. And that's another problem is you get rounding errors. So if you choose to do that method, do not round till the end. Keep all those digits. Okay, so the way I'm going to put this in is I'm going to do it the non-EE way. So I'm going to go 1.2 times 10 caret 6. Okay. Now to do an exponent, you need to do a caret. The caret looks like that's what they call a caret, and it's spelled that. Yeah, it's not the orange Bugs Bunny type caret. Okay, so in fact, what I think I'm going to do is, yeah, I'm going to put it in exactly the way it is up there. Okay, so it's 1.2 times 10 caret 6. Divided by parentheses 6.2 times 10 caret 23 parentheses again 512 times 10 And see, I'm already making mistakes. Because I didn't exit from the exponent version and going down to the real line. So already I've made mistakes putting this in just how it is up there. Now, the way I like to do it is this way. So we're going to go that would be the way I would do this problem. So we're going to go 1.2 EE. When you press the EE key, it shows on the screen as a little bitty E, uppercase E. Everything on the bottom, I'm going to hit the divide key. Everything on the top, I'm going to put the times there. So we have two numbers on the bottom, so it means I can hit the divide key 2 times. Divide, divide. Okay. Now, if I was going to do it using parentheses, I'd go so that's 2 steps. Another step here with the time sign, the number 10, that's 2 more keystrokes, 6. That's just on the top one alone I've saved. So that's why I'm highly encouraging you to get a calculator that's got the EE function built in. So let's see what that looks like. And some of you may already be doing this. That's great. But if you've never seen the EE function, it is really desirable. Okay, so this is the answer my calculator throws up at me. Okay, so most calculators work this way. So if you have an E, that means that's base 10, exponent is minus 15. Sometimes your calculator actually put a little times 10 in there. Depends on your model of calculator. Now, obviously this is not the right answer. Why? Yeah, our sig figs are way off. So we're looking at 2 sig figs. That means we go to the 3rd place. And that's 5 to 9. So we're going to increase that 7 to an 8. So our answer is 3.8. That's our answer. Now, the tricky part is a lot of students will look at this and they'll go on the denominator side there. They're saying, oh, there's multiplication there, right? We're multiplying the 6.2 number by the 5.12. I'm going to hit the time sign. Your calculator, being a dumb shit, doesn't know that that's in the denominator. It thinks it's in the numerator. So what it does is it multiplies by 512 rather than divide by 512. That's why if it's on the bottom, you hit the divide key. You have 2 numbers on the bottom, you're going to be hitting the division key twice. 1 per number in the denominator. Okay? That is a recommended way by our department, Sac City's chemistry department, Tacoma Community College's Olympic Community College. I've taught at all these schools and we all do it the same way. It's a very universally accepted process for doing this. Okay. All right. So let's do one more down here. Okay. So we've got a whole bunch of numbers here. Now, when we get into problem solving, you're frequently going to run into a lot of dividing and multiplying. Sometimes you have a one-stepper, sometimes you have a five-step problem that usually involves multiplication and division. Because when you're doing problems, you're using conversion factors most of the time, which are all fractions. Yeah. Yes. Okay, so we're looking at 6, no parentheses, because as soon as I hit the times key, the calculator thinks it's a parentheses. You don't have to put the parentheses in. It's totally superfluous. We're going to go 6 times 514 EE, change sign 4. Now, on most calculators, 99% of the calculators, there are two minuses. One is subtraction and one is change sign. They're not equivalent at all. Okay, the change sign just changes the sign from negative to positive or positive to negative. The subtracting one actually performs a subtraction. So make sure you differentiate between those two when you're putting these in. So don't be putting in subtract 4 up there. You're going to put in change sign 4. Okay, hit the divide key because it's on the bottom. 624, double E, change sign 14. Divide again, 3.14, EE, 6, enter. I keep hitting this stupid thing. All right, so our answer is our answer is 2 times 10 to the 4th. Yeah, just like that. Okay, so does that make sense when you're doing these problems with multiple parts to it on the computation? And use your advantage on your calculator with the double E. And you can do it without the double E. If you do, every scientific notation number you have down there, you've got to surround in parentheses. That's 2 more steps. Plus you've got to say times 10 plus a caret. 2 more steps. That's 4 right there. And that's per number, per scientific number. So if you've got 3 scientific numbers, that's 12 steps that you don't have to do. Okay, so then questions about this process? For those of you in Saturday lab, you get to practice this today. All right, and the other thing I want to talk about before I move on to problem solving is scientific notation. We talked about this a little bit yesterday. All right, scientific notation, again, the purpose of scientific notation is to make awkward numbers less awkward. Yesterday in lab, someone came upon, the answer was 39 to one of the problems, and she wanted to put it in scientific notation. 3.9 times 10 to the 0, or 1, I should say. And I asked her, which is more awkward? And she said, well, the scientific notation. Well, so I said, then don't put it in scientific notation. But by definition, this is it. There are 2 parts to scientific notation. There's a number from 1 to 9.999, whatever, really close to 10, but not there. And a base 10 exponent, positive, negative, or 0. Okay, you cannot have a scientific notation number without these 2 parts. And secondly, to be proper, you've got to have the 1.999 number. Any other number outside of those, like less than 1 or 10 or more, is not a correct scientific notation. So you got to and that was been some of the challenges yesterday. So for example, this one here, none of these are valid. You should be able to look at these numbers and say, this is not valid because. So like number 1 up there, what's not valid about it? Doesn't have to have a decimal. Yeah, it's not between 1 and 9. I say 9, but it's really 9.9999. Right. So we need to convert it. So we're going to convert the 948 to 9.48. However, when I write the proper scientific notation number there, the number cannot change count-wise. So now we've gone from 948 down to 9.48. Is that number getting smaller or bigger? Smaller, so we have to make up for it on the 10 side. Okay, we made up for it. We divided that by 100, so we have to multiply this side by 100. So 10 squared is 100. So 2 plus 2 is, okay. So make sure when you display a number in scientific notation, it fulfills those 2 requirements. Number from 1 to 9.999, and then the base 10. Now your calculator has base E exponents as well. We're talking about common logs, which is base 10. Okay, does everyone see how I went from the one on the left to the one on the right? Yeah. Say again loudly.
You could check your.
Yeah, that's a good idea. She said you can check this by putting them both in the calculator. And those 2 numbers should be equivalent. Yeah, that's a good idea. I hadn't thought about that. All right, number 2. What's wrong with number 2? Kind of the same thing. So all these have the same problem, is that number from 1 to 9.99. So we've got to convert each one of them. And we convert okay, we're going 1, 2. So we're making it bigger by 100 now. So that means we have to make the exponent smaller by 100. That's 2. So 1 minus 2 is -1. So this section was one of the trickier parts of Lab 1. I know Friday folks have already gone through this, but the Saturday folks today are going to be running into this. Okay. All right. So if there are no more questions, I'm going to start problem solving. We're going to start real simple, and we can get quite elaborate. Now, again, I want to repeat, on your test 1, you're going to have a take-home question, and it's going to be elaborate. You know, it may have 12, 14 conversion steps in it. But based on the first lesson we're going to have on problem solving, it's the same thing, only 14 times. So what's hard about it is not so much the concept, it's just figuring out which conversion factors you're going to be using. Okay, are there any more questions about this conversion? Now, in science and engineering, we use the metric system. And the rest of the world uses the metric system, except 3 countries. us and two little tiny ones, third world countries. And you can thank Reagan for this. During the Reagan years, we were in the process of converting over to metric system. So every speed sign and every place you saw the conversions. My truck is from Canada, so I always have to make sure when I change a battery or something like that, because it always reverts to the kilometers, reverts to Celsius temperature and all this stuff. I have to convert it all back over. Anyway, he decided it was a waste of money and confusing. That was probably when he had starting his dementia. But anyway, so he canned the program. But in science and engineering, we still use the metric system. Not still use it, we use the metric system. All right, so there's a couple parts here now. There are two kinds of conversions. One are by definition, and the other is by measurement. Remember, I talked about significant figures as being a measurement of precision. If you have something that is by definition, for example, this is a hard one. How many are in a dozen? 12. 12.1? No, exactly 12 because it's by definition. So what do you think the precision is on that number? It's infinite. So anytime we have a number by definition, the sig figs on it is infinite. For example, this isn't quite true, but as far as this class is concerned, 1 milliliter of water equals 1 gram. Depends on the temperature and a bunch of other variables and pressure. But as far as our class is concerned, 1 milliliter equals 1 gram. By definition, that means the significant figures are infinite. So when we're using that as a calculation component, because it's infinite, that's the sig figs on that are not going to come into play. So in other words, the sig figs are not one. Sig figs are infinite. So all the boldface definitions here are by definition. So those all have infinite precision. Now this is slightly modified than the one in your lab packet. The one in your lab packet, I don't think it's harder to tell which is by definition and which is not. So this would be a good one to print out and substitute in your lab packet. Okay, so for example, 100 years in a century, infinite. 1 inch is equal to 2.54 centimeters. That's by definition. So the sig figs in that is not 1 and 3, it's infinite. Okay, so that's number one on this page here. Number two is we have a set of problem-solving steps that will get us through to May in this class, through all 5 units. Okay, there are 4 steps. Step number 1 is if there's a chemical reaction, then you have to balance the chemical equation, and this will make no sense until we get to unit 4. So you just need to skip step 1 for now. The next thing is what is given in the problem? What are we trying to calculate? And then we set it up via conversion factors to go from the given to the calculated. Now, one little cute process one of my students invented is well, one more thing. How do we know a chemical reaction is happening? There are about 10 of these, but the most obvious ones are these 4. Okay, gas is produced. You'll see bubbles forming. There's a color change. it gets hot or cold. And what's making all 1 through 3 happen is bonds are broken and reformed. So that's how you know a chemical reaction occurs. If any of those happen, you need to have the chemical reaction and you need to balance it. Unit 4. Okay, so we're not going to have any chemical reactions going on till we get to unit 4. You're going to have physical reactions going on. So in other words, when I take an ice cube and set it on the counter, what does it do? It melts. Is there a chemical reaction going on? No, it's just changing its form or phase. So there's no chemical reaction to worry about there. If we evaporate a gas, there's a lot of physical change kinds of stuff going on, and there's no associated chemical reaction that goes with that. Okay. And we're going to have a series of conversion factors that we work with. Conversion factor is a fraction. Yeah. Up above. Yeah. Yeah. This here, right? Step number 2 is going to be it's going to be in a color. Step number 3 is going to be a different color. So what I'm going to have you do whenever you have a problem is you're going to have 2 highlighters. One is you're going to highlight within the problem's text the given, and you're going to highlight in the text what you're trying to calculate. And then given is going to go on the left, calculate is going to go on the right, and you're going to go from left to right with conversion factors to figure that out with. Everyone, almost without exception, tells me problem solving is hard because it's a word problem. And I remember when I was teaching calculus, it was the same way. Oh, just give me the equation or just show me the integral, I'll solve it. You know, I don't know how to read it. You know, life is a word problem. And as a chemist, as a physicist, as an engineer, or whatever, you've got to go through and pull out the equation. Because otherwise, life is not going to give you the equation. Okay, so I've developed this strategy over the last 2 or 3 decades on this process we go through. And your textbook, TRO, does something extremely similar. Not exactly the same, but it's very similar. He's got what's given. Instead of saying the setup, he calls this a strategy, but it's exactly the same thing. Okay, so let's do a hard problem. Okay, that's a toughie. All right, 15 apples, how many dozen do I have? Right off the bat. Okay, so the first thing is we're going to use green highlighter. The green is that's going to be the given. So what's given in that problem? Okay, the given is 15 apples. Now, the trick to find given is look for the number. The only number in that problem is 15. So that's what's given. And then you look at the associated units that go with it. Okay, so that's given. What are we trying to calculate? Dozen, yeah. So we have right away, the strategy is probably is where you know what's given now. We're trying to calculate. And then step 4 is the setup. Setups are all conversion factors. Conversion factors are fractions. So what conversion factor are we going to use? Well, we can have okay, that's one conversion factor. What's another conversion factor? And this is sort of a trick question. 12 apples equals 1 dozen, right? So notice there, every time we have a conversion factor, we have 2 of them. They always go in pairs. Now, what is the answer to this fraction? 1. Because 5 squared is 25. 25 over 25 is 1. What's the answer to that problem? Same thing, right? So what we do is we take a conversion like this and convert it into a fraction. So again, I'm going to state all conversion factors are fractions. And there are always 2 versions. You have the multiplicative inverse or the inverse of each one of them. So now we're going to have so those are our 2 fractions from this conversion. Now for this to work, these 2 have to be equal. If they're not equal, this inversion doesn't work. You have a question? Just like in lab. Okay, so the question now is, all right, so we've got our given and then we have our calculated. And we're going to use one of these 2 conversion factors times this to get that. So the question now is, most students have, well, Ferguson, which one am I supposed to use? Now, let me show you a way that works every single time. First of all, we have to go back to basic algebra. If I was to multiply A what is that equal to? C. Why? A's cancel, right? So if we look at this differently, the A is functioning as a given. And the conversion factor is giving us what we're trying to calculate. So the question is, going back up here, 1 dozen over 12 apples over 1 dozen, which way are we going to use? What must we use? Right here, we're trying to get rid of the given by canceling. Well, there's 2 versions, right? Be one or the other. So let's look at, okay, if we started with Let's use the top one, 12 apples over 1 dozen. Does that work? Well, it's going to give us a whole bunch of apples over a dozen, but not a dozen. So that fraction inversion is incorrect. Why is it incorrect? The given has to cancel. The given has to cancel every single time. So whatever you start with, make sure the next conversion factor has got the given on the bottom, so they cancel. No exceptions. So you're always multiplying the given by a fraction that has the given on the bottom or on the denominator. And this doesn't matter whether we're talking about quantum mechanics, we're talking about home ec in junior high, doesn't really matter. It's the same thing. So we have to get the given to cancel. That means that so now we want apples on the bottom. And now apples cancel. What's left over? After we cancel out the atoms, not the atoms, the apples, what's left over? Dozens. What are we trying to calculate? Dozens. So this is the correct setup. On a test question, that would be worth 90% of the points. So if this problem's worth 10 points, you get 9 for that setup. Have we used our calculator yet? No. So let's use a calculator. If you use your calculator, you get another 10%. And that includes correct number, correct units. So the actual number itself has to be correct, the number of sig figs has to be correct, and the units needs to be correct to get your 10%. Now, this is why I want you to use detailed setups whenever you do a problem. Because say you came up with the wrong answer. What I would do when I would look at your setup, I'd say, oh, your setup is fine. Or maybe your setup was slightly off a little bit, so I can give you partial credit. So I give partial credit. I cannot give you partial credit if I can't follow your logic. If your setup is all screwed up, you're going to get no partial credit. If your setup is mostly right, I can give you some partial credit. Yeah. Huh? Well, I have to squint at it to see if I can give you partial credit. Depends how differently you set it up. Yeah. I could probably follow that logic and give you, yeah. That's the key, is I'm old. You have to give me a lot of simple steps to follow. And make sure your logic is there, though. And I like to give students partial credit. That's why I don't give multiple choice tests. The answer is either right or wrong. No partial credit at all. My students do always, without exception, better on these complicated tests, believe it or not, than the same version it's in multiple choice. Yeah, because there's no partial credit. And usually if you have something there that sort of resembles a setup, I'll give you like 1 point or so. You know, I'm not going to give you 0 unless it's totally messed up or the units are all missing and stuff. But this is a really simple example of how to set up a problem. So, and then to do this hard problem, How many sig figs is our answer going to be? Two. 15. How many sig figs does 15 have? Two. How many sig figs does 12 apples? Careful. No. Infinite. Remember, that's by definition 12 apples in a dozen. Just like 1 dozen. How many sig figs is that? Infinite. So the conversion factor, the ones I bold-faced, are all infinite. So they don't come into the calculation of your answer. So our answer is going to be 2 sig figs. So our answer is going to be 1.3. It is 1.25 if we actually do it, which is 3 sig figs, not 2 sig figs. Okay, so this process, first thing is identify, assuming there's no chemical reaction, identify what's given, and you can use a highlighter if you like. I think it helps. Next, what are you trying to calculate? Highlight that again in another color. Then what conversion factors do we need to go from the given to the calculated? Now you may need 1, or you may need 2, or you may need 3 or 14. The process is all the same. So any questions about this problem? .3 dozen. So the dozen is the unit. And sig figs is correct. And numerically, it's correct. So all the parts are there. That makes sense? Yeah. If it's by definition, like 12, whatever in a dozen, not 12.1, not 11.9, it's exactly 12. It's infinite. 15 is not infinite. 15 is 2, but it's the 12 and the 1 are the infinite parts. So which is smaller, 2 or infinity? Yeah. Infinity is really big. So gigante. Gigante. All right, so let's do some more here. How are we doing on time here? Okay. How many kilograms are in 3.04 pounds? All right. No chemical reaction. What's given? Look for the number. What's the only number in that problem? Is what? 304. And the associated unit is pounds to that unit. So we're trying to calculate the other unit, which is kilograms in this case. Now we have to figure out, so I'm going to put so pounds on the left, kilograms on the right. So we need a conversion factor to go from pounds to kilograms or kilograms to pound. And that is so what conversion factor are we going to use? So you should need to ask yourself, is there a conversion factor up there with the given and calculated units in it? Well, there's one with Okay, there's one in there that's got pounds and ounces in it. One's got pound and grams in it, but none of them have pounds and kilograms. So which conversion factor are we going to use? Hmm? Yeah. All right. So one conversion factor is going to be that one there, because we go from pounds to a metric system. So that's conversion factor number one. Forgot how many grams it is here. 453.59. So remember, all the conversion factors, you always have two of them. Okay. All right. Does that get us from pounds to kilograms? Well, that'll get us to grams. So at least we got rid of the pounds. Remember, we always have to get rid of that given by canceling out. So the pounds are going to be in the bottom. Okay, so now we have grams. We converted pounds to grams. Now, is there a way we can go from grams to kilograms? What's the relationship between a unit and kilo? 1,000. So there's 1,000 grams in 1 kilogram. So that's another conversion factor. And again, there's going to be two of them. The next question is, which one do we use? Which one do we use so that the gram cancels and leaves the kilogram? Which one of those two? 1,000 grams over kilogram, kilogram over 1,000. What has to cancel? Grams. So what has to be on the bottom? Grams. Now we're there. We keep canceling everything, and what's left? Kilogram. And what are we trying to calculate? Kilogram. So the strategy here is we start throwing in conversion factors that starts canceling out everything until what's left over is what we're trying to calculate. That's the strategy. Now, in this case, it took two conversion factors. Previous problem was one conversion factor. Okay, on one conversion factor problem is if we have both the given and calculated in one conversion factor, it's a one-stepper. Usually it's not a one-stepper. Usually it's multiple steppers, okay? So here we have an intermediate calculation on grams. So if you can link one conversion factor with one of the units in it and you can find another conversion factor that has the other unit in it, probably there's a way to put those two together to give you your answer. And again, this is the essence of something called the official name is called dimensional analysis. So your textbook calls it. The other one, some people call it unit cancellation. To me, unit cancellation says more because it says how to do it. Cancel the units. Okay, so what are we doing on sig figs on this problem? Going to be 3. And usually if you just go through, now on this one here, the 453.59 was not bold-faced. So that means it's not by definition. So that means this has got 5 sig figs. And 1 kilogram is 1,000 grams by definition. So answer is going to have 3 sig figs. So we're going to go 304 times 453.59, all divided by 1,000. So we're looking at now see my calculator is set up for scientific notation, so it goes E0. Remember, E0 is 1. So 138 kilograms, 3 sig figs. So we have the numeric answer, we have the unit, and the sig figs. Now, the way I set up problems on a test is the value of the problem is how many steps it's going to take. Yeah. How would you type it in? I would go 304 times 43.59, divide key 1,000, enter. Now, don't put ones in. If you're OCD, put the ones in. If you're not OCD, don't have to put the ones in. All right, so does this problem make sense? Yeah. It is. Yeah. That's why I put infinite up there. See the sideways 8? That's infinite. That's measured. And it's not on the conversion above, it's not boldface. Now I will give you that on your tests, that conversion table. So, yeah. Into the calculator? Yeah. Yeah. Use whatever that I give you. Oh, sorry. Yeah, I'm doing unit cancellation. So I'm crossing out the grams. Yeah, that's my haste there. Okay, so does this make sense? Now, some of these problems you're going like, why are we going through all this hassle? Just divide by 12 or whatever. Because every single problem we're going to do in here is going to be harder than the apples to dozen problems. This way, it's a strategy to get around this problem of, I hate word problems. I don't understand word problems. I'm not good in English, whatever. This starts with a strategy. What's given, what trying to calculate, what are the conversion factors to get us there? Every single time. When we get into unit 4, we're going to add another step. That's the, we're going to go from multiple steps. Then we're going to do problems that take up a whole page, one problem. But again, it's step by step, little by little. And it's unit cancellation the whole way. And that's the biggest challenge in 1A, Chem 1A, is what we're doing now. My students over the summer, you'd think someone taking a class at University of California, Davis would know how to do unit cancellation. No, they didn't. That's because you're in a class of 800. That's what the beauty of community college is. When I took Chem 1A, there were 72 lab sections. 72. Not one or two. Big difference. And graduate students taught the lab sections. They were called TAs, teachers assistants. And the problem with graduate students is some of them were from other countries, and some of them, particularly for Chem 1A, were brand new to the country. So this is not being judgmental, but their English was horrible. And you had to get through that lab section with someone you couldn't understand very well. So it was a real disadvantage to having all those lab sections. And some programs you were required to be a TA, other ones were optional. One I was in was optional. Okay, are there any more questions about this problem? It'll be the one up above. The one this one here. Well, on test 1, yes. On test 2, you're not going to need it because we're doing something else that doesn't require, conversion. The same with unit 3. Unit 4, well, the back end of unit 3 and the whole thing in unit 4 that's probably the hardest unit is unit 4. Okay, so let's do some more here. So you're going to have to get comfortable with the metric prefixes: kilo, centi, milli, micro, giga, tera, all those prefixes. So that's a good flashcard deal. You don't want to be looking them up each time. I'm going to give you the conversion table, but still, it's better to just know them. And in 1A, you're going to have to know them. Okay. All right. Let's do one more. What time is it? It is. Yeah, let's break this one problem down, and then we're going to go to lab. Okay. So plane travels from San Francisco to LA in 1.54 hours. We burn 3.45 pounds per second. That's of jet fuel. How much fuel does the plane use? Now, this is similar to one of the take-home problems I gave for my Unit 1 test. Whenever you combust anything, this is for Unit 4 take-home problem. Whenever you burn anything, you produce two things: carbon dioxide and water, assuming it's not a messed up jet in terms of the ratio of oxygen to fuel. Assuming all that is perfect, you end up creating water and carbon dioxide. So tomorrow morning, I want you to start your car and run around the back and look at your tailpipe. And you're going to have something dripping out of that tailpipe. Guess what it is? Water. Exactly. Because when you burn gasoline, you produce water and carbon dioxide. Okay, you go back to your tailpipe half an hour later, there's no water dripping out. Where'd all the water go? Huh? Yeah, it's steam now, so you don't see it. Still there though. Who knows what a contrail is? What's a contrail?
Same thing, but not the jet engine. Pretty much just the water vapor being burned up and it freezes the atmosphere.
Exactly. During World War II, towards the end of World War II, they were bombing German cities and Japanese cities, and they would have like 2,000 bombers up there. Each bomber had 4 engines with 4 contrails. So the whole sky was crisscrossed with these contrails. So there's no sneaking up because your planes lit up all these white trails coming out the back. And gasoline, jet fuel burns, produces water and carbon dioxide. The water on these planes are like 35,000 feet. It's very cold up there. So it goes to ice. And that's what you're seeing, the little ice crystals up there. It's pretty cool. Okay. So anyway, the problem was very similar to this. I said a plane takes off from Seattle, lands in Los Angeles. It burns so much fuel per hour. How much ice do you produce? That was the problem. So anyway, all right. So let's look at this problem now. What's given? Okay, someone said hours. What else? Huh? What does the word per mean? P-E-R. You see this word all the time. What does it mean? Yeah. Ratio, yeah, or fraction. Exactly. Good. All right. So we have a fraction within our problem. What do we know fractions usually are? Conversion factors. So the conversion factor is built into the problem. So that's the given, 1.54 hours. And what are we trying to calculate? Fuel. When I say how much, what is that? What are the units associated with how much? Pounds, or how much in metric? Not, it's grams, yeah. So we want to know grams of fuel. So we start with okay, so where do we go from here? Well, do you know any conversion factors that have hours in it? Right? Okay, that'll cancel our hours. Now we have minutes. We need seconds. Do we know a conversion factor that has minutes and seconds in it? Exactly. Okay, now we know How many seconds are in 1.54 hours? Is that all we need to do in this problem? What else do we need to do? One more. We're going to use our conversion factor. So what's going to go on the bottom? Seconds. And 345. Go on the top. Now we have pounds of fuel burned. Now, if I was going to give this on the test, I would say how much fuel I put in parentheses G for grams. Here it doesn't say G, so you could leave it at pounds or convert it to grams. If we're going to convert it to grams, we would need something to go from grams to pounds. We've already done that. The 453.59 grams per pound. So now we have grams of fuel. So this is a four-stepper, but the concepts are exactly the same. We're canceling units to get what we desire in the end, unit-wise. And we're using fractions the whole way. So what is our answer going to be in unit-wise? Well, we have 3 there. Three sig figs there. What about 60 minutes in an hour? How many sig figs is that? Infinite. By definition. What about 345 pounds per second? 3. And the 453.59, and that's 5. So our answer is going to have 3. And notice on this one, there's all ones on the bottom. So whenever you have ones, you don't have to put those in. So we just have a bunch of multiplications. We're going to multiply 154 times 60 times 60 times 345 times 453.59. That'll be grams of fuel burned. Now, lab 2, you'll practice this a lot. That's the whole focus of lab 2, is this guy here, type problem, okay? And we went from a 1-step problem, 2-step problem, 4-step problem. And this kind of problem you can expect on a test. Okay, you have some real simple ones, and you'll have 1 or 2 like this. Okay. All right, so yeah. Yeah, let me multiply it out. So that'd be the answer. What? No. That would be smiley face. No, that's the reason we should put grams. All right, so that's it for today, you guys. I'll meet you over in the labs, lab 106 at 1:30. Yes, the homework, if you go to module, you'll see problems at the end of the chapter. And there's quite a number of, and then the answers are in the back of the book. And those are practice problems. And what's nice about Unit 1, we have 2 really good dry labs that give a lot of practice as well. So between the dry lab and the, which you are going to get credit for, between the dry labs and the textbook problem, there's a fair amount of practice. You should do fine.